When we started with differential equations, we started with qualitative analysis, and I want to do the same thing here. Systems are even more difficult in general than single differential equations because you're trying to solve multiple equations at once. It's a pretty hard thing to do. Anything that is nonlinear in particular can become really, really difficult to get an exact solution, if not impossible. So doing qualitative analysis is immensely important. I want to consider this situation, autonomous systems. So I have two, say, populations, if we're thinking about mathematical biology, P and Q. They both depend on time, they both change in time, and I have their growth rates isolated. So everything on the right side of this doesn't involve derivatives. The derivatives are only on the left. This is a first order system, and this is an expression in P and Q. So the independent variable t doesn't show up on the right side. This is an autonomous system of differential equations. For this particular setup, there's a lovely qualitative tool called the phase plane. And if you're thinking of the phase line that we've done before, well, this is exactly the extension of that to a two-dimensional system. So it's going to use the same kind of ideas, but it's becoming a lot more complicated now with multiple equations. In the phase line, I drew a real number line and labeled things on it. Well, now I have two functions, so I'm going to draw R2, and I'm going to label the axes P and Q for the two functions I'm measuring. Then I'm going to look at these expressions on the right side, and I'm going to set them equal to 0. This is like solving equals 0 with the right side of the phase lines to find the steady states. So I'm going to get the locus f of 0 and the locus g equals 0. I'll draw those two loci. Those are going to produce some lines or curves in this R2, and those are going to be called nullclines. The nullclines of the first one of P or of F, and the nullclines of the second one of G or of Q. The intersections of the nullclines, the place where the F and G nullclines meet each other, are going to be your steady states. That's places where both the rates of change are 0. So points in the space, values of P and Q, where the system is momentarily completely steady. It's not going to change. All right, so we have our steady states and we have our nullclines. Nullclines break up R2 into a bunch of regions. And in each region, I'm going to determine the sign, positive or negative, of these right-hand expressions f of g. F is related to P, which I've sort of labeled as the x-axis. So it's going to relate to whether something is going positive or negative horizontally. G is related to Q, which I've labeled as the y-axis. So that's going to be interpreted vertically. So I'm going to draw direction arrows. If F and G are both positive, then both horizontal and vertical are increasing. I draw an arrow up and to the right. And likewise up and to the left, down and to the right, down to the left, depending on whether F and G are positive. Then from those direction arrows, I'm going to try and make paths that follow the two populations, the two functions around the steady states. How are they going to behave near the steady states? And since I'm now talking about paths in R2, I can get all sorts of behaviors. This is the main idea. Find the nullclines, find the intersections, find the steady states, label the directions between the various nullclines, and then use those directions to try and guess what the functions are going to do. Then, based on that, we would like to talk about the stability of the steady states. And unlike phase lines where this was pretty clear, stable, unstable, partially stable from the left or from the right, here we can have all sorts of behaviors. These are the 6 behaviors that happen just for linear first order equations, and I'm going to talk about these more in detail in the next video. When we get to nonlinearity, all sorts of other behaviors can happen and it gets even more complicated. But that's the main idea. Using those directions, trajectories, can we talk about around a certain point, a certain steady state, is the system going to be stable or unstable, and how so?